Motor overload protection is required per National Electrical Code Section 1910.305 Roman 3. National Electrical Code Section 1910.305 Roman 3 states that all motors installed after January 1, 1999 shall be protected against running overload by one of the following means. Firstly, a separate overload device that is responsive to motor current. This device shall be selected to trip or reset at not more than the following percentage of motor nameplate full load current: 125% for motors 1 horsepower and smaller, b 115% for motors 1 horsepower through 100 horsepower. Secondly, a thermal protector integral with the motor, approved for use with the motor. It protects on the basis that it will prevent dangerous overheating of the motor due to overload and failure to start. And thirdly, a protective device integral with a motor that will cause the motor to stop operating before dangerous overheating due to overload and failure to start occurs. It's crucial to understand what constitutes acceptable motor overload protection. In the scenario presented, utilizing only the main disconnect fuses does not satisfy the NEC requirements for motor overload protection. Fuses are primarily designed to protect against short circuits and ground faults, which involve very high currents. Overloads, on the other hand, are lower level increases in current that can occur over a longer period. These overloads, while not immediately catastrophic, can cause the motor to overheat, damaging the windings and potentially leading to premature failure. The NEC mandates specific devices designed to detect and respond to these overload conditions. These devices are designed to trip or reset at a predetermined percentage of the motor's full load current, providing a much more sensitive level of protection than fuses alone. The two primary types of overload protection devices are circuit breakers and thermal overload relays. Circuit breakers are electromechanical devices that trip when the current exceeds a certain level. They offer both overload and short circuit protection. Thermal overload relays, on the other hand, are specifically designed for overload protection. They use a thermal element that heats up in response to the motor current. When the element reaches a certain temperature, it trips a set of contacts, disconnecting the motor from the power supply. The selection of the appropriate overload protection device is crucial for ensuring the motor's safety and longevity. The NEC provides specific guidelines for selecting these devices, based on the motor's horsepower and full load current. For motors 1 horsepower and smaller, the overload device should trip or reset at no more than 125% of the motor's nameplate full load current. For motors 1 horsepower through 100 horsepower, the overload device should trip or reset at no more than 115% of the motor's nameplate full load current. In the case of a 208 volts 3-phase 1/4 horsepower motor, the full load current can be determined by referring to NEC Table 430.248. The table lists the full load currents for 3-phase alternating current motors. For a 208 volts motor, the full load current will be approximately 1.52 amps. Once the full load current is determined, the maximum allowable trip current for the overload protection device can be calculated. For a 1/4 horsepower motor, this would be 1.25 times the full load current. So, 1.25 multiplied by 1.52 amps equals 1.9 amps. Therefore, the overload protection device should be selected to trip at or below 1.9 amps. It's important to note that the NEC also allows for the use of thermal protectors integral with the motor. These protectors are designed to prevent dangerous overheating of the motor due to overload and failure to start. If a motor is equipped with an integral thermal protector approved for use with the motor, a separate overload protection device is not required. However, if the motor does not have an integral thermal protector, a separate overload protection device is mandatory. In the given scenario, the customer's intention to use a maintained push button to start and stop the motor without any overload protection other than the main disconnect fuses is a clear violation of the NEC. A maintained push button simply provides a means of turning the motor on and off. It does not provide any protection against overload conditions. The main disconnect fuses are designed to protect the entire circuit from short circuits and ground faults, but they are not sensitive enough to protect the motor from overloads. To comply with the NEC, the customer must install a separate motor overload protection device, such as a circuit breaker or thermal overload relay. This device must be selected to trip at or below 125% of the motor's nameplate full load current. Additionally, it's important to ensure that the overload protection device is properly sized for the motor's voltage and current rating. Using an undersized or oversized overload protection device can compromise the motor's safety and performance. An undersized device may trip unnecessarily, causing nuisance outages. An oversized device may not provide adequate protection, allowing the motor to overheat and potentially fail. In conclusion, the NEC requires motor overload protection to prevent overheating and potential damage to the motor. Fuses alone are not sufficient for overload protection. A separate overload protection device, such as a circuit breaker or thermal overload relay, must be installed to comply with the NEC. The overload protection device must be selected to trip at or below 125% of the motor's nameplate full load current for motors 1 horsepower and smaller. By understanding and complying with these requirements, you can ensure the safe and reliable operation of your motor. Let's delve deeper into the specifics of motor overload protection and how it relates to the National Electrical Code. As we established, simply relying on the main disconnect fuses for a 208 volts 3-phase 1/4 horsepower motor does not meet the requirements outlined in NEC section 1910.305F Roman 3. This section specifically addresses the need for dedicated overload protection devices to safeguard motors from sustained overcurrent conditions that, while not immediately catastrophic like a short circuit, can lead to overheating and eventual motor failure. Now let's break down the implications of this code requirement and how to achieve compliance. Firstly, understanding the difference between overloads and short circuits is paramount. A short circuit is a high-magnitude, instantaneous fault that causes a rapid and substantial increase in current flow. Fuses and circuit breakers are designed to quickly interrupt this high current flow, preventing damage to the circuit and equipment. An overload, on the other hand, is a lower magnitude of a current condition that persists over a longer period. This can be caused by factors such as excessive load on the motor, a locked rotor condition, or voltage fluctuations. While the current increase is not as dramatic as in a short circuit, the sustained overcurrent can cause the motor windings to overheat, leading to insulation breakdown and eventual motor failure. Secondly, the NEC provides specific guidelines for the selection and sizing of motor overload protection devices. These guidelines are based on the motor's horsepower rating and full load current, as indicated in the motor's nameplate. For motors rated 1 horsepower or less, the overload protection device must be selected to trip at no more than 125% of the motor's nameplate full load current. For motors rated between 1 horsepower and 100 horsepower, the overload protection device must be selected to trip at no more than 115% of the motor's nameplate full load current. These percentages are crucial for ensuring that the overload protection device provides adequate protection without causing nuisance tripping. Thirdly, there are several types of overload protection devices available, each with its own advantages and disadvantages. The most common types include thermal overload relays and electronic overload relays. Thermal overload relays utilize a bimetallic strip or a multi-alloy to sense the motor current. When the current exceeds the set point, the bimetallic strip bends or the alloy melts, causing the relay to trip and disconnect the motor from the power supply. Thermal overload relays are relatively inexpensive and reliable, but they are also subject to ambient temperature variations and may not provide the most accurate overload protection. Electronic overload relays, on the other hand, use electronic circuitry to sense the motor current and provide more precise and reliable overload protection. Electronic overload relays can also offer additional features such as adjustable trip settings, current monitoring, and communication capabilities. Fourthly, the NEC also allows for the use of integral motor protectors. These are thermal protection devices that are built directly into the motor windings. Integral motor protectors are designed to sense the temperature of the motor windings and trip the motor if the temperature exceeds a safe limit. If a motor is equipped with an integral motor protector that is approved for use with a motor, a separate overload protection device is not required. However, it is important to verify that the integral motor protector meets the requirements of the NEC and is properly sized for the motor. Fifthly, it's important to consider the specific application and operating conditions when selecting motor overload protection. For example, if the motor is subjected to frequent starting and stopping, or if it operates in a harsh environment, a more robust and reliable overload protection device may be required. In addition, if the motor is part of a critical process, it may be desirable to install redundant overload protection to ensure that the motor is always protected. Sixthly, proper installation and maintenance of motor overload protection devices are essential for ensuring their effectiveness. Overload relays should be installed in accordance with the manufacturer's instructions and should be regularly inspected and tested to verify their proper operation. In addition, it is important to ensure that the overload relay is properly sized for the motor and that the trip settings are correctly adjusted. Seventhly, let's revisit the specific scenario involving the 208 volts 3-phase 1/4 horsepower motor. As we determined earlier, the full load current for this motor is approximately 1.52 amps. Therefore, the overload protection device must be selected to trip at no more than 125% of this value, which is approximately 1.9 amps. This means that the customer must install a separate overload relay or circuit breaker that is rated to trip at or below 1.9 amps. Eighthly, it's crucial to understand the role of fuses and circuit breakers in motor protection. While fuses and circuit breakers provide overcurrent protection, they are primarily designed to protect against short circuits and ground faults, not overloads. Fuses and circuit breakers are typically sized to carry the motor's starting current, which is significantly higher than the full load current. Therefore, they will not trip on an overload condition unless the overcurrent is severe enough to cause a short circuit. Ninthly, the NEC also addresses the use of manual starters and magnetic starters in motor control circuits. Manual starters are simple on/off switches that do not provide any overload protection. Magnetic starters, on the other hand, incorporate overload relays that provide overload protection. If a manual starter is used, a separate overload relay must be installed to comply with the NEC. Tenthly, it's important to consult with a qualified electrical engineer or electrician to ensure that the motor overload protection system is properly designed and installed. An experienced professional can assess the specific application and operating conditions and recommend the appropriate overload protection devices and settings. In addition to the points already discussed, several other factors should be considered when selecting and installing motor overload protection. Firstly, the ambient temperature can affect the performance of thermal overload relays. If the ambient temperature is significantly higher or lower than the temperature at which the relay was calibrated, the trip point may be affected. To compensate for this, some thermal overload relays have ambient temperature compensation features. Secondly, the altitude at which the motor is operating can also affect its performance. At higher altitudes, the air is thinner, which can reduce the motor's cooling capacity. This can lead to overheating and premature motor failure. To compensate for this, the motor's overload protection may need to be derated at higher altitudes. Thirdly, the type of load that the motor is driving can also affect the selection of overload protection. For example, motors that drive constant torque loads, such as pumps and compressors, require more robust overload protection than motors that drive variable torque loads, such as fans and blowers. Fourthly, the duty cycle of the motor can also affect the selection of overload protection. Motors that operate continuously require more robust overload protection than motors that operate intermittently. Fifthly, the presence of harmonics in the power system can also affect the performance of motor overload protection. Harmonics can cause the motor to draw more current, which can lead to nuisance tripping of the overload protection. To mitigate the effects of harmonics, harmonic filters may need to be installed. Sixthly, it's important to periodically inspect and test the motor overload protection system to ensure that it is functioning properly. This should include checking the trip settings of the overload relays, verifying the continuity of the overload relay contacts, and testing the motor's insulation resistance. Seventhly, in addition to the NEC, other standards and regulations may also apply to motor overload protection. For example, the National Electrical Manufacturers Association NEMA publishes standards for motor control equipment, including overload relays. The Occupational Safety and Health Administration (OSHA) also has regulations regarding motor safety. Eighthly, it's important to keep accurate records of the motor overload protection system, including the type of overload relays used, the trip settings, and the dates of inspections and tests. This information can be helpful in troubleshooting problems and ensuring that the motor is properly protected. Ninthly, the cost of motor overload protection should be considered, but it should not be the primary factor in the selection process. The cost of a motor failure can be significantly higher than the cost of a good overload protection system. Tenthly, it's important to stay up to date on the latest developments in motor overload protection technology. New and improved overload relays are constantly being developed, and it's important to be aware of these advancements in order to ensure that the motor is properly protected. Let's discuss some real-world scenarios that highlight the importance of proper motor overload protection. Firstly, imagine a scenario where a manufacturing plant relies on a 208 volts 3-phase 1/4 horsepower motor to operate a critical conveyor belt. If the motor is not properly protected against overloads, a prolonged overcurrent condition could cause the motor windings to overheat and fail. This could lead to a shutdown of the conveyor belt, disrupting production and resulting in significant financial losses. Secondly, consider a situation where a commercial building uses a 208 volts 3-phase 1/4 horsepower motor to power a ventilation fan. If the motor is subjected to frequent starting and stopping, or if it operates in a dusty environment, it may be more susceptible to overloads. Without proper overload protection, the motor could overheat and fail, leading to reduced ventilation and potentially compromising the air quality in the building. Thirdly, picture a scenario where a wastewater treatment plant utilizes a 208 volts 3-phase 1/4 horsepower motor to drive a pump. If the pump becomes clogged or experiences a blockage, the motor could be subjected to an overload condition. If the motor is not adequately protected, the overload could cause the motor to overheat and fail, resulting in a disruption of the wastewater treatment process and potentially leading to environmental contamination. Fourthly, imagine a situation where a food processing facility relies on a 208 volts 3-phase 1/4 horsepower motor to operate a mixer. If the mixer becomes overloaded due to excessive ingredients or a mechanical malfunction, the motor could be subjected to an overload condition. If the motor is not properly protected, the overload could cause the motor to overheat and fail, leading to a shutdown of the mixing process and potentially compromising the quality of the food product. Fifthly, consider a scenario where an agricultural operation uses a 208 volts 3-phase 1/4 horsepower motor to power an irrigation pump. If the pump is subjected to a heavy load or experiences a malfunction, the motor could be subjected to an overload condition. If the motor is not adequately protected, the overload could cause the motor to overheat and fail, resulting in a disruption of the irrigation process and potentially damaging crops. These real-world examples demonstrate the critical role that motor overload protection plays in ensuring the reliable and safe operation of motors in various applications. By understanding the NEC requirements and implementing proper overload protection measures, you can prevent motor failures, minimize downtime, and protect your equipment and processes. In conclusion, motor overload protection is not just a code requirement. It's an essential safety measure that protects motors from damage and ensures the reliable operation of critical equipment. By understanding the NEC guidelines, selecting the appropriate overload protection devices, and implementing proper installation and maintenance practices, you can safeguard your motors and prevent costly downtime. Always consult with a qualified electrical professional to ensure that your motor overload protection system meets the specific requirements of your application. Remember, a small investment in overload protection can save you from significant expenses and disruptions in the long run. The information presented here provides a comprehensive overview of motor overload protection and its importance in complying with the National Electrical Code. By applying these principles, you can ensure the safety and reliability of your motor-operated equipment.